So, okay, guys, welcome back to day 9 of simple harmonic motion. This is probably the last day. I'm going to discuss the problems that are just asked to me, all the doubts that you people asked, and I'll also discuss the damped oscillations, damped and forced oscillations. I mean, there won't be much of a discussion. That will be the end of the topic. We'll end the day with that topic. So let's look at these questions. Let's start with the short answer questions. I think all the questions in the first page are like pretty easy. 1, 2, 3, 4, 5, 6. Do you want any discussions? If you want, please let me know. But the first question that you asked from this page, this short answer questions, was the seventh. So let's look at that question first. In the measuring time period of a pendulum, it is advised to measure the time between consecutive passages through the mean position in the same direction. This is said to result better accuracy than measuring the time between the consecutive passes through extreme positions. Explain. What is your argument, Mazida? Mazida, you gone unmuted again. Guys, did you get the question? In the measuring time period, it is advised to measure the time period between passes through the mean position. He is saying it is better that you take the time period between the mean positions than you take the passes through the extreme positions. Like you take the time in between extreme and extreme. Is it better, or is it better to take the mean position?
So
What
it
is
is
your?
better in extreme because mean is
Sir,
tough
it makes
to
the same
calculate.
result.
But it is saying it chases in the opposite direction, right? In the opposite way.
Sir, I think even no, sir. Extreme positions is only the better accuracy.
Yeah, I even thought the same thing, but I've never seen.
Sir,
I've
it's
never come
because
across.
of because of our reaction time, sir.
You think it is about the reaction time, but
Yes,
even
sir.
in the
Like,
reaction time, it is easier to check whether it is at the extreme position, right? Rather than taking the mean
sir,
position.
extreme position we'll have to drop it and start at the same time, sir. Whereas if it is at the main position, sir, we get a fraction of time to actually
Excuse me, sir.
take a look and then
Sir,
start.
consecutive passage through mean position doesn't mean a whole time period.
At least you
It's
get
only
the
half of
half
it.
time period, right? It's not about the
Yes, sir.
whole time period. It is about clicking at the right point. That is what I'm thinking. Okay,
Reaction time.
let me discuss this question with someone else, because I think it's the other way around. So let me discuss this question with someone else and we get back to this thing. Mazda, what's the next question that you asked?
Ninth one, sir.
Ninth one. Can the potential energy of a simple harmonic motion be negative? Will it be so? Choose the potential to zero potential at some point and the other mean position. What?
Yes, sir.
Can the potential energy be in a simple harmonic motion be negative? Will it be so if we choose zero potential energy at some point, then other than mean position? Yeah, is this a possible case? If
Yes,
we
sir.
Yes,
take the
sir.
extreme position as a zero potential thing, if we take the extreme position as a zero potential point, at the mean position, the potential has to be lesser, right?
Yes,
So
sir.
they will be
Sir,
negative.
not extreme. If we take the whole system and put it in some minus 1,000 like that, it will
Yeah,
be
yeah, it's
negative
always
only.
possible. It's always possible. Yes. So ninth is possible. Then
13th one, sir.
which one?
13th.
13, right, good. So a hollow sphere is filled with water is used in a bob of a pendulum. Yeah, this is an interesting question, guys. Assuming the equation of simple pendulum valid, the distance between the point of suspension and the center of mass of the bob, effective length. If water slowly leaks out of the bob, how will the time period vary? This is a very interesting question. Watch it, guys. Let me discuss it on a separate page. This is a like quite a common question. When you have a pendulum filled with water, let me use a different color. Filled with water, the center of mass is here. Let us consider a case when the most of the like half of the water is drained out. The center of mass is clearly somewhere around here. Now let us consider a case when it is completely empty. The center of mass is back at the center. If you clearly observe, the center of mass goes down and then comes up. Again, whenever you try to find the time period of a compound pendulum, it is all about the distance in between the center of mass, like as I mentioned. So the length increased and then length gone back. You clearly observe that. Length has increased and the length has gone back. So the time period 2 pi root over L by G, it increases then decreases. That is the point. Mazida, do you get it now? Mazida, she's gone.
Excuse me, sir.
Can you
Yeah,
say that again, sir?
Sir, it increases and suddenly decreases, right, sir?
not suddenly. As the water is like very little, the center of mass tends to go down, and after some time it will actually go up. Mazida?
Yes, sir.
Excuse me,
I understood.
Yeah. Aditya, what's your doubt?
sir. But water might will also have mass, no, sir. If I use the other equation, then it should be other way around.
No, you're not considering the water that is left, okay? We're only considering the mass that is hanging.
Yes, sir. The mass will be less, no, than compared to the first case if we
But 2
see.
pi root over L by G doesn't have anything to do with mass.
So mass won't affect here.
So mass won't affect here. It's the position of center of mass that affects.
Okay, sir.
Okay?
Sir, if we use M by K instead of L by G,
Why do you make such stupid statements sometimes? It is for a spring block system. 2 pi root over M by K is for a spring block system. Why? Why do you do this to me?
just for seeing, sir.
Oh, come on. Such a pain you are. Now, so we didn't discuss the question number 16. We cannot discuss it right now because I didn't discuss the damped oscillations or the forced oscillations yet. Let me discuss this question number 16 right after the end of the topic. Okay. Now, anything else from these questions, from the first few questions? Anybody? No? Then I'm going to shift to objectives, objective questions. Any questions from objective on this page? Anybody? No? Okay. Any questions from this page? Anybody?
So objective 2.
Okay. You don't have any questions from this part, right?
No, sir.
No. Objective 2. Any question?
So 6, 7, 8. Can you just explain them?
Yes, of course. Because it's not much of a big deal. Okay. You always should be ready to talk about like a particles in the main position. It is somewhere around here going away. Now the displacement is positive, the velocity is positive, but the acceleration is negative. Okay, let's look at the same body, but it is coming back like somewhere around here. Now the displacement is still positive, but the velocity negative, the acceleration is also negative. So you have to look at all the different cases, like the two cases on this side, the two cases on this side, and even the cases at the mean position when the velocity is zero. Sorry, the velocity is maximum, acceleration is zero. At the extreme positions, velocity is zero, acceleration is maximum. Look at all the specific cases, and if you clearly observe all the cases, I'm pretty sure you can answer all the questions. All the questions that are right here. Now, like look at sixth question. Which of the following quantities are always negative? If they're in the same direction, dot product is positive. If they're in the opposite direction, dot product is negative. Getting my point? Mazida, why are you going mute? If you're asking a doubt, please stay unmuted. Or whatever. Look at question number 7. It is again the same thing, which is a positive, which is negative. So look at the points when both are in the same direction, dot product is positive. When they're in the opposite direction, dot product is negative. Okay.
Yes, sir.
Yeah. So look at 8th again. He's talking about the cross product now. The cross product is always zero in my opinion because they're either 0 degrees or in the positive or 180 degrees, right? So it's always zero.
Yes, sir.
For all the cases, it's always zero, right?
Yes, sir.
If you are clear about this, I'm going to move to the exercises. Are there any other doubts? Anybody? Nope. Now coming to this page, I believe I left out these two questions, 14 and 15 and 16 also. Now all the three questions. Yeah. Who's that? All the three questions, 14, 15, 16, they all deal with the same idea about shift of the mean position. Okay, let me look at this question. Question number 14. I'll try to explain question number 14. 15 is a little similar. Let's see if we can do it. Let me delete this thing. Reading question number 14. A small block of mass m is kept on a bigger block m, which is connected to a vertical spring. The system oscillates vertically. Find the resultant force on the smaller block when it is displaced through a distance x above the equilibrium position. Now, again, find the normal force on the smaller block at this position. Find the force smallest in magnitude. Okay, what can be the maximum amplitude in which the block can oscillate together? Let us look at all those questions. Okay. This is a bigger block. This is a smaller block. We are not even, oh, wait a second. Yeah. We're not even dealing with the old equilibrium position anymore. Like we don't even need the old equilibrium or new equilibrium. This is the equilibrium position, final. Let us say this is the final equilibrium position. And about this equilibrium position, the body is oscillating. The body is oscillating about the equilibrium position only. This is the final equilibrium. It is oscillating with some minus a to plus a. Let's talk about it. So when it is displaced by some distance x, when it is displaced by some distance x, at that point, it has to have some velocity and also has to have some acceleration. That acceleration must be proportional to minus x. Okay. Since it is spring k, the acceleration must be, sorry, the force must be equals to kx for sure. Okay. But here is the interesting bit. Let us consider when the blocks are here. I'm drawing that thing here. M. We all know the acceleration is omega square x. It must be minus omega square x at that specific point. When they're here, the acceleration is downwards, a, which is equals to minus omega square x. He gave this value, x away from the position. Acceleration equals to minus omega square x. So there is a spring force acting on the lower block, and then there is gravity mg, capital Mg, small mg gravity, normal force, normal force. Both the normal force acting on it in the same direction, in different directions. The thing is, guys, if you look at this whole system, it is accelerating downwards with this acceleration, a equals to minus omega square x. Or you can write a equals to minus k by m plus mx. You can say that because omega is nothing but k by m plus m. You can say that. But the point is, look at the body separately. There is a spring force acting. There is gravity acting. And there is normal force acting. So if I have to write the equation first just for this body, the lower body, mg plus kx plus n, all the forces are acting downwards equals to m into this acceleration. For this body, mg is downwards, normal force is upwards equals to mass into this acceleration. Can we find the normal force from this? Since I have the acceleration, I have an, can I find the normal force? Anybody? Aditya, can we do it?
Yes, sir. If we substitute these things
The
in that, we'll
acceleration there,
find.
yes, we can find the normal force. That is the force he's asking. When the blocks are oscillating, like this, when it is here or when it is here, like you need to be careful. Okay, when it is below the point, the acceleration is upwards. When it is above the point, the acceleration is downwards. You need to be careful and change the directions. In the problem, did he mention it's above or below? Distance above the
Above,
equilibrium.
sir, above.
Since it is above, what I did already is wrong, right? Okay. Now, here is an interesting bit. As they're oscillating, Aditya, what does your intuition tell? At what point the normal force will be minimum? The normal force in between them will be minimum. Can you say anything?
Can I tell, sir?
Yeah.
At the higher position, it should be minimum, sir.
Exactly.
So when
At the
Ka is
highest
greater
position,
than mg,
it should be at the highest position, it must be minimum. At the lowest position, it must be maximum. Like intuitively, we
Yes,
can
sir.
say, or if you really want to do it, you can find this equation and actually look at the equation and tell at what point it is minimum or maximum. Like you put this value, right? Check for all the x values, you will find at a specific point it will be maximum, and at a specific point it will be minimum. For sure,
Yes, sir.
you can easily get that. Okay. Now, so what he's asking is what is the minimum value? So try to look at the positive extreme point, try to look at the positive extreme point and find the normal force. Now in the same question, in the third question in the same book, what can be the maximum amplitude at which point they can oscillate together, which means if it oscillates way too much, like again, if you can intuitively look at it, if the blocks oscillate way too much, there is a point where they might break separately, which means
Yes,
all
sir.
you have to do is at the amplitude take normal force 0 and try to find the amplitude at that point. Take the normal force 0 and
Even
try to find the
the equations only we play like
one
n
doubt,
is equal
sir,
to 0,
in
sir.
this.
Yeah, tell me.
Sir, after this amplitude, for the blocks to separate, again some separate amplitude will be needed, right, sir?
Yeah, the amplitude, once they separate, I mean, this is the breaking point, like this is the limiting condition. At this point, they just might break. But if the amplitude is beyond that, it won't even be an SHM. It will oscillate in a very random manner, like they separate and then it comes back and falls on the block, and the oscillation will be a very strange thing to talk. So at this point, at the point of maximum, A max, like the maximum amplitude, they tend to break. That's all. They don't really break. They tend to break the contact. Okay.
Sir, so in this question, we'll just have to take that case in which the normal force is equal to 0, right, sir?
Yeah. If you take the normal force case where the normal force is 0, you're talking about the limiting condition. Okay.
Okay, sir, got it.
Sir, here can we just say that Ka is equal to mg?
Yeah, it is actually.
Okay, sir. So
You
just one doubt in this. After this point, only the capital M will be going in the oscillation, right, sir?
if the
So
amplitude
will
if
that
the
affect?
amplitude is more than that, yes, only capital M will go in
Yes,
oscillation.
sir.
But the
So will
small
that
M will
affect the
again
amplitude
come
and
back.
also?
The small M will again come back and fall on it, right? So there's a chance of that also.
Oh, okay, sir.
Right. Now look at the question number 15. It is exactly almost the same thing, except everything is happening at an angle.
Yes,
So
sir.
I'm,
Nothing
I'm
changes.
suggesting you to look at this question again and try it. Okay, everything is happening just like the way, but it's happening at an angle. So instead of mg, you'll have mg sine theta and things like that. And also he might talk about the new equilibrium, old equilibrium positions like that. Again, you have to find the maximum point at which it might break, I guess. Yeah, two springs separate. They will
Yes, sir.
separate only when the normal force is 0. So it's again the same thing. Okay. Now coming to 16th question, I already discussed, but which part do you want me to discuss again, Aniket?
So from D, sir.
Find the amplitude. What do you mean find the amplitude? Find the
No, sir,
potential.
from there I have doubt.
Like what?
D, E, F, sir. The 3 bits I got doubt in the answers.
Like you didn't get the answers?
Yes, sir. I didn't get the correct answers, sir, and some doubt.
I mean, like it's not a new concept to teach. So then we'll decide it in the doubt session normally. Okay.
Okay,
So it
sir.
happens with me also, sir. One question I got different answer in this, but the format is different given in the question, sir. So
Maybe
it's
you
just
could be
because
making
of
a mistake.
format also, sir.
You could simply be making a mistake. Okay. I look at question number 23. We've already discussed 23, which is quite an easy thing, but look at question number 24. If only this has moment of inertia. If you stick to your basics, that question is very easy.
Yes, sir.
Okay. If you stick to your basics, the question is very easy. You shouldn't just let the question take you by surprise. That's all. You displace it by X. Try to look at the restoring force, and that is all. Now try to look at the restoring force. Here the restoring force is not kx, I'm sorry. Try to look at the restoring force, which is nothing but tension. Here there will be kx. Okay, but how do I relate all the things. Okay, so let us look at all the problems. Here tension equals to MA. I'm not considering Mg because there is already some T naught which balanced Mg. We've already talked about it. So that is why I'm not taking Mg anymore.
Yes, sir.
There is already some equilibrium position. So there is already some Kx naught. These all things already balanced each other. So this is an additional tension, additional expansion. We've already talked about this kind of ideas, right? So I'm only going
Yes,
to
sir. We
write.
just have to neglect. We have to write
Yeah,
it
yeah.
and
We
neglect
just
it, sir.
we just take all those equilibrium cases out and we solve the next problem normally. T equals to ma, and for this pulley, what can we write? T minus k, so k equals to I alpha and a equals to r alpha. If you do this, you will get acceleration proportional to minus x. If you solve these three equations, just put it there and try to solve a equals to r alpha, t minus kx and all. You will get again an acceleration proportional to minus x, and you'll get it. It is like an angular SHM only, like except this pulley is executing angular SHM, this is executing normal SHM. You get it? Okay.
Yes, sir. So I
20.
had one small doubt.
Yeah.
Sir, I did the other way around, sir.
So it's a doubt like A is proportional to minus theta we take for angular, right, sir? So in some places they wrote like x by L instead of theta.
Yeah.
Yes, sir. So like how did we get that? I didn't understand.
Why? Come on, man. You are a legend. Sometimes this is x, this is L, this is theta. X equals to L theta. This is like the most basic thing that you need to learn in the
Oh,
physics.
in that way. Okay, sir.
Wow, you are a legend. Someday I might even kill you. Like if you are in a class, I might kill you someday. Look at this problem 26, okay? If it moves like this, just try to look at the center of mass. Try to solve this whole problem in the perspective of a compound pendulum. Look at the center
Sir,
of
it is
mass.
moving like that.
Yes. Oh, you thought it is moving like this?
Yes,
Yes,
like
sir.
in front and back, it is moving, I
No,
thought.
it cannot oscillate like this. It is oscillating as the body is staying stable. Like
So in
if
indoor
it is in the
methods,
mean
sideways
position,
or
it will be like
front
this.
back.
In the extreme position, it will be like this. At the other extreme, it will be like this. So it will oscillate like
So
this.
why can't it be the way we thought?
The string cannot expand, right? If you want it to expand, oscillate like this, the string has to expand. It's not expanding. The string has to.
No, like it will come towards me, then go back and then come towards me, back and
It
forth
doesn't really
motion.
matter. It doesn't really matter. You can think about that in that manner also. If it is coming towards you, like yeah, I can't draw a 2D diagram. If you do solve that also, it's the same thing. Like it, you can take the sidewards oscillations or frontward and backward oscillations also. It's the same thing.
So which is easy, sir?
No, it's the same thing. It is exactly the same thing. It won't make any difference at all.
Okay then, sir. I will
Okay.
try both the method then.
So that question is clear. 31 I've already discussed yesterday. Guys, question number 30, you simply take this question as this. These two questions are completely similar. Can I tell you why? Since there are
Acha,
no
it is joining and okay.
since there are no horizontal forces in between them, if only there was friction, they're not similar. But since there is no friction at all, there are no horizontal forces in between the bodies. If there are no horizontal forces in between the bodies, it doesn't matter if they're like this or they're like this. There will be vertical forces, but we are not talking about vertical oscillations here, right? Since we're only
Excuse me,
talking
sir.
about horizontal oscillations, we don't have to care about
Sir, but when we are taking the velocities, we have to take relatively, right, sir?
no, completely take them separately. You don't have to consider the relative velocities at all. Try to solve them separately. If he is asking the relative velocity, then try to write the relative velocity. But as long as you're solving this problem, this is a worked out problem, like I mentioned already. It is there in a worked out problem. Try to look at this question just like this. Okay. Again, this is not the solution. I'm asking you to look at it that way so it becomes easy. Okay.
Okay, sir.
Yeah. Now, after that, I think that's it. I mean, yeah, question number 41 is a very, very long question. I'll try to discuss it in a separate session, because I don't think it needs that much of attention in a class like this. We'll be wasting a lot of time. Yeah, the
Sir, previous page more two doubts were there.
which one?
Sir, I think
The
50
mind
and
out you
51.
told that it's like physical pendulum
He
only.
asked 49 and 50. They're basically physical pendulums or compound pendulums. So
50 and 51 I asked, sir.
yeah,
They were
50.
compound
50 and
pendulum you
51, sir.
told.
Same I sent you also, sir.
Yeah, they're compound pendulum problems. Try to look at them as
Oh, okay,
compound pendulum. It's as if a body is oscillating. It's not a single mass that is oscillating. Try to look at that as a body oscillating. Try to use the same formula. Time period equals 2 pi root over I by mgd. You will definitely get it.
Yes, sir.
Now look at 54. I don't understand why you didn't people get it. I think we've gone into a different dimension. No, we are back. Like what happened in 54? Like which part did you not get? Is it about writing the moment of inertia? Oh, he asked the tension. This is an interesting question. I'm sorry, I didn't see whether he asked the tension. Look at this question. So, as you see, if I look at the top view of this thing, like they will basically oscillate like this. About this main position, it will oscillate like this. Not up and down. I'm talking about a top view. So if we look at the body in the top view, the string will be at this point.
In horizontal plane, sir.
Yeah, in the horizontal plane, they will oscillate like this. Okay. So when they're at an angle theta naught, this is the theta naught is the amplitude. The body is oscillating about this point. Okay. Now he didn't even ask the time period in this thing. When it comes to the mean position, it will have some angular velocity, right? Because of this angular velocity, it will experience a, what do you say, mr omega square, m into this r into omega square. He's asking the tension value. The tension equals to mr omega. So how do you find omega? Omega is nothing but maximum angular velocity. I mean, at the mean position, which is nothing but, oh, let's not write it as omega. I'm sorry. I might confuse you again. This omega is this different, right? Let me take another omega.
Sir, we have to include mg also in this.
No, mg is acting vertical, right? This is happening in a horizontal plane. You don't have to mention the mg.
Okay, so because in answer they gave, sir, mg.
What?
Yes, sir, in the answers in the end it is given mg.
Wait a second. What tension did he ask? Find the tension in the rod as the system passes through the mean position. Question number 54, there is an mg there. Oh, there is a shear stress also. Acha, he's talking about that. Okay, let me discuss this mr omega square. Omega is the maximum angular velocity, which is equals to theta naught into omega. Like I mentioned, V max equals to A omega. Omega max equals to theta naught into omega. You have to find omega, like the time period thing. So theta naught into time period is, if I remember it correctly from yesterday's problem, how much was that? Torque equals to k theta. So alpha equals to k by I into theta. The moment of inertia of this thing is what? Is there anything? Moment of inertia of these two bodies, m at a distance r. So you have to write 2 into mr square moment of inertia. You put it there, you find the angular velocity. That is a horizontal force. Now there is a vertical force also for this body. Oh, such a tedious problem again. So there is that horizontal mr omega square, and then there is gravity. The resultant of these two is nothing but the tension in the rod that is developed. Okay. So yeah, Sharath.
So the moment of inertia is 2 by 5 mr square for each ball, right?
Did he say they're spherical balls?
So they mentioned that they're balls. In the diagram,
Small
they're
balls. He
spherical.
mentioned very small, so you don't have to do that.
Okay, sir.
Point mass, sir.
Yeah, point mass. You can simply consider them as point masses. All right. I think we are done with this. Please ask the rest of your doubts in a doubt session tomorrow. And in the doubt session, as in Harish Khan sir's doubt session, I will start a new topic most probably tomorrow. Okay. So I will end
So
this
what about
topic.
DPP?
I will end this topic with the discussion of damped oscillations.
Sir, DPP?
DPP also, please ask Harish Khan sir. We can't use time for that. Okay.
Okay, sir.
Please ask your rest of your doubts to Harish Khan sir. You have a plenty of time there. We don't have the time here because that is why I'm switching back to the teaching. Okay. Watch this thing. A spring block system. Good. But there is friction. What will happen? The body will oscillate for sure. But as it oscillates, it simply slows down and comes to rest. So
Yes, sir.
that thing is called as damping. Except it's not just friction. Sometimes, even though you take a simple pendulum, it's oscillating. There is a force of viscosity, drag force, viscous drag force. Because of that, the oscillations keep decreasing and it stops at some point. So that is called as damping.
So what does damping mean? The word?
Damping is something that slows it down. It makes things die down. Like the things
Okay, sir.
which are oscillating, which are moving, it slowly dies and comes to rest. Okay, that is
Okay,
a
sir.
thing, that is a property called damping. Okay. Yeah. So he doesn't consider this case in your books. The case that they don't talk about a constant friction. They only talk about viscous force. That viscous force is proportional to velocity. So here the force that is acting on a body is not just kx. There is also some constant, some viscous constant into v. Now this is where the problem starts. Okay. The force is nothing but mass into acceleration equals to minus kx minus bv. Now in a single equation, you have displacement, velocity and acceleration. If only I write it properly, I know you people are already a bit worried, but this is a double differential equation. Now solving a double differential equation is not even in your syllabus. It comes in your engineering syllabus. Okay. But he solves it for you and gives an equation saying x equals to, I don't remember what it is. Wait a second, I can. Amplitude into e power minus bt by m a sine omega t or something like that. I'll tell you what it is. Okay, you might not understand what happened here, but I'll tell you what it is. Take this e power minus bt by m part left out and look at a sine omega t plus delta. So he is talking about an SHM. He is talking about an SHM only, except there is a function, an exponential function, whose graph looks like this. There is an SHM equation multiplied with this equation. Can anybody guess what it looks like? Do you
So I
people
do
know?
not understand the question, sir.
Okay. Let me start with this thing. If I give you an equation saying y equals to a sine theta or y is equals to a sine omega t, what's the graph look like?
So it will be like sine with a
Yeah.
and minus a as the
What if
maximum
I
minimum
multiply it
point.
with 10?
So 10a will be the maximum minimum
Yeah,
point.
so it simply looks the same except the amplitude is amplified. Agree?
Yes, sir.
Not uniformly amplified, right, sir?
Uniformly amplified, yes. But what if I give you an equation saying y equals to x sine omega t?
Sir, at each point, sir, the graph will keep decreasing, sir, from its
Or
Yes,
initial
sir.
point.
sorry, y equals to t sine omega t. Or leave the time part. Y equals to x sine x. It's as if I'm trying to multiply. Somebody is in the waiting room.
At each point it will multiply,
Sir, it
sir.
will keep
But
increasing, sir. The
depending
amplitude
the
will keep
sign value, it will
increasing.
increase, decrease. That is very
No.
Sir, one
The
unpredictable.
small
the
question.
sign value basically will be the same thing. The x value y equals to x is like this. So it will multiply with very small values here, very small. And as we are going to the bigger values, the other sides, the sides on the right side get really big. So you will get a graph, something that looks like this.
Like a
Because
Wi-Fi
the
symbol.
beginning parts were multiplied with very small values. These parts were multiplied with this. These parts are multiplied with very some big values. So the graph looks like this. Do you understand it?
Yes,
Yes, sir.
sir.
Yes, sir.
So it'll actually look like it is sandwiched in between y equals to x and y equals to minus x, something like that. Okay. Now, if only I have a graph which is like this, e power minus x sin x, it is as if I have to take this equation and put it in between this. So the first beginning values are multiplied with very high, and as we are moving, the multiplication factors are like getting very, very small. So the graph looks like what?
That
It looks
Wi-Fi
like the
symbol
exact
which is
opposite.
reverse, I'll say.
Does it not look like a damped oscillation?
Yes,
Yes, sir.
sir.
Like it's
Exactly. So
dying
that
out
is what it
after a
is
function of
there.
time.
That is what it is there in your. Wait a second. It's actually there in your textbook. A lot of people tend to ignore it, but I would not suggest that because it is very easy. They don't give you anything in the problem. They simply give you this is the viscous force. So mass into acceleration equals to minus kx minus bv. That's what he wrote there. He solved the equation. Look at it, amplitude sine omega t multiplied with that exponential function. Minus bt by, did I say m? You actually have 2m,
Yes,
okay?
sir.
You actually have 2m there. Try to remember this equation, that's all. So every time they give
Excuse
you
me,
a
sir.
every time they give you a viscous force, try to write this equation, that's all. Now, they might simply ask you this equation in the worst case, in a damped oscillation. Okay. Yes, they might ask you to remember the what do you say, the change frequency also, even the frequency changes. I'm sorry about that. Like it won't be the normal frequency. Even the frequency changes a little, and it is not easy for you. I mean, like it's not easy to simply explain it because he didn't even mention that, right? He clearly said this equation can be solved using the standard methods of calculus. Yes, yeah, standard methods of calculus, but it is not there in your standards right now, solving a double differential equation at this point. So that's what we get, and this is the equation that we get. So this is the graph that we get. Even look at this. This is the amplitude equation. This is how the amplitude decreases as it is dying down. The amplitude slowly decreases. That is the thing that he wants us to learn. Any doubts? Yeah, there will be a lot of doubts, but all you need to understand is this equation. You should be able to write this equation here and this part. A little understanding. That's all. I am.
Sir, I have one doubt, sir.
Yeah.
Sir, even I have one doubt.
Yeah.
Instead of this viscous, if it is like friction,
It must be a constant value. Then it will give you a different answer again. So that part is not discussed in your syllabus.
okay, sir.
It should
Sir,
be
and in
discussed,
that
but it
graph,
is
it is showing like it's increasing again at
what?
the
Where is
end.
it increasing? No, it is dying. It must die.
The curves, sir, right there look like they are
Yeah,
increasing.
there maybe, but no. The reality is it should die.
Okay, sir.
Sir, I want that few questions regarding this damp oscillation. Like after every one oscillation, it will decrease or uniformly it will decrease, sir?
No, it depends on this function here, right here.
Uniformly, right, sir?
It would, you shouldn't say uniformly. It is more like an exponential function.
Okay, sir.
You call it as
And
an
one more thing.
exponentially decreasing value.
And so, what will be the relation of time period with this, sir?
The time period is right here. The frequency is here,
Like,
so the time period is here.
I want to compare one point where like t is equal to 1 second, and other point t is
No, the
equal to
time
10
period
seconds.
stays constant. That's the best part. Like, look at this. The frequencies stay constant. Everything, every value is constant here. The new time period, the new frequency is a constant value. So the time period for every oscillation is constant. That is a good thing. Okay,
Okay.
that doesn't change. Yeah.
So, like, if we try to compare the original graph for SHM and this graph, sir, like at each and every point there'll be some variation, right? Instead of just a variation at the amplitude.
Yeah. There is like even the frequency has changed, right? So there will be a difference. The
Excuse me,
frequency is
sir.
clearly changed.
Sir, the time period for every half oscillation will be same, right, sir? Not for full.
No, even for half or even for full. Oh, no. It is a full. It is for full only. It is for full.
The curves are becoming smaller, sir. So
But you shouldn't
But
really
the
call it
velocity
as,
will
wait
also
a second, you
decrease, no,
shouldn't
sir.
really call it as time period, right? Because it's not a periodic function at all. It's not even a periodic function, right? You're not even getting
yes,
the
sir.
same values in the further cases.
But still, we are considering as an SHM, na, sir. So we
Yeah, we
have to
shouldn't, we
use it
shouldn't, we
sometime.
shouldn't. Don't define the time period for this thing, okay? Let's just
Yes,
sit
sir.
with the frequency. It is not the right thing to define the time period for this, okay?
Yes, sir.
Now look at forced oscillations. This is even worse. Not just kx and viscous force, they put up a sinusoidally varying external force to keep the oscillations going on, because since the oscillations are dying, as we looked at it, the oscillations have died down, right? They put an external force so that the oscillations keep going. What are the losses that this is causing? They'll try to match up with this. Now, it is very, very difficult to understand this bit, to understand the amplitude, to understand the frequency and all, to even to understand this part, it is very difficult. But I can tell you one thing. I can only tell you one thing about the forced oscillations. The frequency that they give here, the frequency that they give here, let us take a spring block system. Let us take a spring block system with friction or with viscosity, with a viscous force which is varying with minus bv, and they put up an external sinusoidal force f naught sine omega t.
Sir, sinusoidal?
Sinusoidal as in the force is varying with the time. It's not a constant force. If only you put a constant force, it will simply change the what? It will simply change the mean position. That's all. But they put an external force
Yes, sir.
which is also varying. Now, it is
Okay, sir.
very, very important that this frequency was matching the natural frequency of the system. If it is not matching, the oscillation is a very ugly thing to watch. It's as if the block is trying to accelerate, this force will stop it. The block is trying to decelerate, the force will try to accelerate. So the oscillation gets really ugly. It is not a beautiful thing to watch. If only you match the exact frequency, like if the system has a frequency, it's as if the system is trying to go that way, the force will push it. The system is coming to try to come back, the force will actually pull it back. So if only you're matching the natural frequency of the system, the oscillation looks really beautiful. And if only you exactly match the value, that is called as a resonance. We will come back to this word a lot more, but in further topics, it makes more sense. Not right now, but in further topics, it makes a lot more sense. At resonance, the oscillation will be a beautiful thing. It'll have the maximum amplitude. Even you have a graph here. You look at this graph. At the resonance frequency, you'll have a maximum amplitude. Before that and after that, like if you don't maintain the frequencies properly, this is what you get. The oscillation is a very ugly. You won't even get a proper amplitude. That is the thing. You get the point?
Sir, I did not get anything, sir.
Sir, but close to the correct frequency, we will get very correct ones, right, sir?
Yeah, exactly. Like the system already has a specific frequency, right? Like a spring block system already has a specific frequency saying root over k by m. If only you're providing the external force with the same frequency as when it is going to the extreme, the external force is also pushing it to extreme. When it is coming back, the force is also pulling it back. It is as if Aditya, you're trying to dance. Okay. Like you're trying to
Okay.
dance, and the dance is a basic shuffle thing. Okay.
Yes.
You go left, you go right, you go left, and you go right. Now you're dancing with a girl, let us just say. You're blushing, I understand, but just imagine
No, sir.
dancing with
I'm first of all, I don't dance only.
let's just imagine you're dancing with a girl. Now imagine that girl is also in the same frequency with you. When you're going to left, the girl is also going to left, and you're both are coming to the mean position at the same time, and both are going to the extreme at the same time. What will happen? Your oscillation look very simple, like both are supporting each other with the same frequency. But you
Sir,
imagine you try to go right and she's trying to pull you to left. What will happen now?
what should happen, sir? I'm
We
still
leave
not
and
able
go,
to
sir.
understand anything, sir.
Okay, leave that part then. If you didn't understand, if
Excuse
you
me,
don't
sir.
feel that part, leave that part.
Sir, if we keep the wrong frequency, then will it continue to damp or will it be stable?
No, it won't be stable. It will damp. And like I'm telling you, it's a very ugly thing to watch. You can't even understand what's happening if it is not at the same frequency.
So, like in a long time period, will it be the same or?
No, you can never know. You can never really tell if the frequency is not the same. It's not a beautiful thing to see. It's not even a uniform thing to watch.
Okay, sir.
It will be like Aditya dancing with a girl who hates him. You don't want to watch that, right?
Yes,
If
I
it's
want to
I
as
watch.
too
if
don't want to dance. You're making me dance. I don't want to dance.
whatever. But if you didn't understand this bit, leave this bit out because it's a very, like I said, this is a thing with the damped and the forced oscillations. The chances of getting a problem from this thing is a very low chance thing. So don't really worry about it. I understand for a lot of people, today's class is
So
like
in
learning.
advance, will it come?
I don't think so. In advanced, I don't think forced and damped oscillations are there. Let me check it. Let me check the syllabus and talk about it. Okay.
Because, sir, like after you mentioned the word resonance, I just completely got out, sir.
You didn't understand the idea of resonance because you never danced with a girl. Try to dance with
I
a girl.
understood, sir,
I
even
don't, sir.
without
I
dancing.
don't want to also. I'm
Okay.
better alone for
Okay.
a while.
It's fine. Okay, then. So yeah, operation successful, but patient is still infected. Who said that? Sharath. Yeah. So let it be, guys. Let it be like that. Let me just end today's class. It's already 8 o'clock. We will discuss further things tomorrow. Please
So,
make
one
sure.
small doubt.
No, please make sure you clear all your doubts before I start tomorrow's class. Okay.
Oh, okay, sir.
Thanks so much and bye bye.
Thank you,
Thank you,
sir.
sir.